Done and done. All right. So we learned what language model is, and then what was language model? What did the language model do? Right, so the language model was a big box that we were creating. The text as input, a sequence, let's say a sentence or something as input, and then it was supposed to give us a one number. Then the number corresponds to how probable that given sentence is under the data that we have used to train this language model. Then we talked about two different ways to build a language model at a very high level of abstraction. One was so-called auto-regressive model, where we try to rewrite the joint probability over the entire sequence that consists of the multiple words or the tokens as a product of the conditional probability of each and every variable given all the previous variables. It was really just using the definition of the conditional probabilities, or sometimes some people refer to it as chain rule of probabilities. And that one was really nice because we were effectively turning this problem of unsupervised learning, where there's no label, into a series of text classification. So each and every conditional probability or the distribution we had in this auto-regressive model corresponds to a classifying any given prefix or any given subsequence of the sentence into one of the potential next words. Right? So that was the idea of using the text classification. The other approach to language modeling, which we're going to cover later in this course, was the latent variable model, where we're going to introduce a new variable. Let's call it Z, but we never really observe. Our data set doesn't really have Z there, but we're going to introduce it artificially, and then going to assume that every single word we see in the sequence is conditioned on the Z, the latent variable. And then the idea is to marginalize out this latent variable to induce a very complicated distribution over sequences. And you can imagine that we really do need a very complicated distribution over these sequences, right? And so we decided to look into the auto-regressive model first, and that's going to be largely about 2/3 of this course entirely, this auto-regressive model, because it's really nice. We just need to decide on the order of these words. And often we can just use whatever the order that you feel very natural about. It's often going from left to right or right to left in a monotonic order. And once we decided to do that, it was just how to train a text classifier. But then obviously we talked about some issues, right? The difficulty is that this text can be really, really long. And then the exact way to solve the problem of text classification, surprisingly, turned out to be to just count. How often did this input appear to belong to one of the categories that is the next word? And that's a perfect way to solve this problem, right? Because the input space is discrete. So if you could actually figure out for every possible value in the input space to which class they belong to, then we can solve the problem. Except that this space is really large. This space is so-called combinatorial. We start with a very simple, let's say, vocabulary of small words, right? So we have a vocabulary of unique words, and then we combine them, right? We combine them in order to build up this text. What that means is that this space is pretty large. It's combinatorial in the sense that we have vocabulary of the finite number of tokens, but we can combine them however we want. So the size of the space grows exponentially with respect to the number of tokens that you add to this sentence. And what it leads to is that the number of all possible text snippets is much larger than the size of the data set. In fact, it's much larger than the number of the atoms in this universe. So effectively, we have a pretty strict upper bound on how well we can do in terms of just counting for each of the cases in which class it belongs to. So that was the issue of the sparsity. And in order to address the sparsity, we thought, okay, so maybe then we need to control the size of this input space. And that is how we decided to introduce the idea of the nth-order Markov property into this auto-regressive model, saying that the conditional distribution over the next word, given all the previous words, can be very well approximated by the conditional distribution over the next word, given only a few preceding words. And then the few can be as small as 4 or 5. And then you probably saw last week at the lab session that, indeed, these small numbers still works reasonably well to a certain degree. But obviously, that one has big issue. So let's try to, play a game ourselves. And then this is the example that we talked about. So in Korea, half of the residents speak, and then now you need to guess what the next word should be. Then if you have a bit of, let's say, knowledge about the word and common sense, then you guess that is Korean. But then, if I ask the same question by just telling you that half of the residents speak, and then trying to guess the next word, then it becomes much more difficult to guess what the next word could be. Any language can essentially be the answer there, right? Because I haven't really specified which geographical location or which group of people that I'm talking about. So what that means is that making this kind of mental Markov assumption is always limiting. So we wanted to solve the problem of sparsity by creating another problem. So we solve the issue of the sparsity, but we create another problem. So then before we continue with this recurrent language model that's going to solve this issue of the short context, right? At the end of the last week's lecture, we talked about where does this issue of sparsity comes from. There seems to be a number of reasons, but they're all interconnected or interrelated with each other. Then one of the main reasons is because we don't know whether a given, let's say, given pair of words or given pair of prefixes or the given pair of phrases are similar to each other. I'm just wondering, I just realized that I had this muted, but no one actually has complained so far. I don't know. Can you all hear me from the other side? Can you raise your hand? Well, obviously they can't hear me, but okay, so they somehow can hear me. But indeed on the podium, in fact, there is a notice saying that there is some issue with the audio in this lecture hall, and then they know it, they're trying to fix it. So I guess that is the reason. So you can all hear me as well, here as well, right? Okay. All right, good. So the issue was that so one of the major factors behind this issue of sparsity is that even though some of the words or some of the phrases are really, really similar to each other, how we define or how we decided to represent those tokens, that was to use the one-up representation, effectively told us that they're all dissimilar from each other to the same degree. Then because of that, we cannot really utilize any of the knowledge that we know about other similar phrases in estimating this conditional probability given a new phrase that are very similar. And then somehow we were able to do that, right? We talked about what was it? Was it a lion chasing, right? So the lion is chasing a llama versus lion is chasing a deer. And then somehow, I'm pretty sure not a single one of us has seen a lion chasing llama. I don't think anyone in the history of humanity has seen it because they just don't live in the same continent. But we're all pretty much pretty confident that the lion is chasing a deer is pretty similar to lion is chasing a llama. And then no one is going to say that, okay, the sentence lion is chasing a llama is improbable. Right? No one would say that. It's reasonably probable because a llama, just like a deer, has 4 legs, they're herbivorous, and they look actually pretty similar to each other. So unsurprising. So from there, we decided that so then what if we use these machine learning algorithms that relies on the word embedding and class embedding? Instead of counting all possibilities, we're going to just train this text classifier because what was the first observation about the oral regressive paradigm of your language model? Was this really just text classification? So if you use the text classification that we learned earlier in the course, like in the second lecture, then this text classifier is going to automatically learn the representations of these words in the source side as well as the words in the target side, so as to reflect the similarities among all these discrete tokens. And then thereby, you can in fact capture the use the notion of the similarity in order to estimate the conditional probability of the cases or the engrams that in fact never appear in the training set. So if you count it, we would have actually never estimated any kind of probability assigned to that one. And we also learned about how that can happen, right? So there was that, and then how that can happen just automatically appeared. All we had to do was to ensuring that the probability, log probability of a correct observed sentence is maximized. And by doing so, we were automatically telling our model to find the representations that are reflecting the semantic similarity or the similarities in the context of two things, right? One is the data that we were using, corpus that we were using, and then second thing is under this distributional hypothesis that we talked about at the very beginning of the lecture. Right? So things that appear together, they must mean something similar. Right? So that's where we ended last week, and then we're going to talk about now with that one. Can we actually extend it beyond just n-gram language model? So we were still sticking to this Markov assumption and say that we want to do the n-gram language modeling, but counting is not that great for the purpose of because of sparsity issue. Let's use a neural network or the classifier. Now today we're going to again use the neural network, but we're going to ensure that this neural net is able to process a unbounded context. So the idea is to use the unbounded context. So language model that can handle unbounded context of phrases. So this is today's goal. So let's just rewrite this chain, the auto-regressive model. So the idea is to say that the probability of sequence that consists of the t many discrete tokens, so each and every one of them is going to be an element from this finite set that is we refer to as vocabulary, can be written as the product of the conditional probability of the word that times that t given all the words, all the previous words. So this is just a definition of the conditional probability as we talked about. And although I'm going to just use the left to right in this case, but this order can be arbitrary. This order can be arbitrary. We just need to fix it in advance just because we're going to use one classifier at every location. So the order has to be somehow consistent across the different sequences, but this order can be arbitrary. And if time permits, near the end of the course, I might actually be able to tell you about what if we want this order to adapt depending on the content of the sequence. That's not that difficult. You have to write it down and work with it, although it's pretty useless, but we can talk about it later. And then now, what was the thing that we did for the Markov assumption or the n-gram model was to say that each of these conditional probability can be very well approximated by just looking at n or n plus 1 previous tokens, right? So this was the n-gram language that we looked at yesterday. But this is clearly not that great. We just talked about the example. And well, that's actually an interesting thing because I'm not entirely sure if more than half of the residents in Korea do speak Korean. I gotta check up the statistics, but I think that might be true with a high probability. So let's look at the final version, the feed for. So I think in the last sessions we called it feed for n-gram language model or the n-gram feed for language model. In the original paper, this approach was proposed in 1999 by Yoshua Benjo and his collaborators. It was called neural probabilistic language models. But again, names or the dimensions, what kind of the convention you use the column vectors, row vectors, pretty much details. When you code it up, you gotta be very careful. When you write down, when you derive the mathematics, but when you think about the concepts, you can abstract them out. So I'm going to just call it for now. Neural probabilistic language model. And neural probabilistic language model has 3 components, right? So what is it? So let's write the neural probabilistic language model here. All right. So what are the 3 components? First one is that how to represent the input n-gram, input phrase. So we're going to embed the input phrase. So either n-gram or n-1 gram, I just can never actually count. But. And then how we're going to embed it is to simply concatenate the word embeddings. Imagine it like that. So we have the word embedding of the t minus nth word. And we have the word, and then you have to go all the way to the word embedding of the xt minus 1 transpose and then transpose. Then this is going to be n times d large vector. What is n? N is going to be the number of the words in the input, or that's the number of the preceding words that we consider. And then d is the dimensionality of the word embedding. So that's the first thing. What is the second thing? Because we never wanted to work with a linear model in the case of the language model, because it, we know now, based on our lecture from the text classification, that the linear models are very, very limited. Unless we come up with the amazing, let's say, features. But coming up with amazing features for a new problem that you run into is more difficult than just letting your neural network figure out what those features are. So we're going to stick to the second, let's say, the paradigm of just learning everything. So we have this concatenated, let's say, representation of the source. What we do is we're going to multiply some Wayne matrix to this concatenated representation of the prefix, and then add some bias, and apply some point-wise nonlinear function. And then one of the most widely used one is the rectified linear units. But there are many different, let's say, nonlinear functions that you can use, and almost all of them are already implemented in PyTorch, TensorFlow, Jackson, and also you can use it. But back then, in 2000, the most popular one used to be hyperbolic tangent function. And if you recall how the hyperbolic tangent function looked like, no one does, right? No. But it's essentially like the sigmoidal function. Again, if you know sigmoidal function, which again, no one really teaches you at any point, is that it's bounded from below by -1, and then it's bounded from above by 1. And then when the input is 0, it's 0, so hyperbolic tangent. And then in the limit of the infinity, it's going to converge to 1. In the limit of minus infinity, it's going to converge to -1. It's a really nice kind of, let's say, smoother version of, you can think about the step function, right? So the sign function. If it's negative, you're going to get -1. If it's positive, you get 1. Except that the function is not really nice to work with, because the gradient or the derivative is not really well defined. It's 0 everywhere. And then at 0, it's not even defined there. So we're going to work with hyperbolic calculus. So it's a very well used pointwise nonlinear function. And then we are going to say that there are d prime many neurons. That is, this input was the n by nd dimensional. Then this w has to be d prime by nd dimensional matrix. And then this b, the bias, is going to be d prime dimensional matrix.
Good question.
Yes.
The x's here are words. Right?
X's here are words. Although they could very well be, let's say, amino acid, or the ATGC, right? So the DNA, whatever you want. Yes. But for the sorry,
Would it also be classes?
it could very well be classes. In fact, you can actually learn to capture the class information or the class, let's say, dependencies by using this kind of model. But then, if you think about it, in language model, in order regressive language model, that's exactly what we're doing. Because classes are also just words. Yes.
What is the thing before the d, not the d in like the first real numbers?
This one?
Yeah.
ND.
Oh.
Yeah. So n is the number of words. Here, are there n already n plus 1 or the n minus 1? N plus 1. Or n? No one knows. Isn't it like the course? Is it a grad course in NYU Center for Data Science? All right. Another question.
So are the e's summed over in the vector?
No, it's not sum. It's just concatenation. We're just concatenating them.
We sum them over like in the second lecture, right?
Oh, so we sum them over when we want to use the continuous back-of-word representation, but we're not using the continuous back-of-word representation because that one is going to ignore the order of the words in the prefix. And then in the case of the language modeling, we talked about it last week that if we ignore the order, we can't really do language modeling. We gotta know the order of the words that appear.
Why did you stop at T-1?
Because we want to predict T.
All right.
Mhm. It's confusing. It's definitely confusing. We're going to get more confusing in 2 weeks, but for now, we always look at the previous version. Okay. So now we have a non-linearly transformed representation of input, right? So this is a non-linear representation of input. And what do we need in the final stage? Because it's just a text classifier, we need to have a function that computes the score. Right? And then the score is the score of the xt. So the one particular choice of xt given xt minus 1 to xt minus n to xt minus 1. And this will be the class embedding. So this is going to be class embedding of xt transpose h. So this is the representation we got from the nonlinear layer in step 2, plus the bias associated with the xt, or the class bias, you can call it like that, right? Now, here's the one thing that you want to look into with this W. And if you think about the size of this W, as we just talked about, is the d prime by n times d. And what this means is that the size of this weight matrix grows as you increase the n in this n-gram language model. So if you wanted to do 32-gram neural probabilistic language model, your weight matrix is going to be 32 times larger than just doing unigram language model. Yes.
Wait, so why is it that that line has a total dimensionality of d prime? Because we have our W matrix times.
Yep. This embedding of the input sequence, which was ND dimensional vector. So we have the D prime, ND by 1, so we get the D prime.
But isn't each of those, each of the like xt, x
Each of these will be the D dimensional. We just
right, so
consider
aren't we, isn't that a matrix?
No. So we're sticking to the column vector in this lecture, this course. So column vector transpose row vector. We just put them next to each other.
I see.
Detonate, transpose it
I
back.
see. So we're concatenating it into one dimension.
Yes.
Okay.
That's why it's the RD, ND, not N cross.
Okay.
So that's an issue. Although there are some people who have actually trained successfully 32-gram language for language model. There's a guy named Holger Schrenk in France. I think he's a bit extreme. So he actually trained a 32-gram neural probabilistic language model, but he doesn't do that anymore because at some point you notice two things that are missing here. One was the big issue of growing number of the parameters as we increase the size of n. And the second issue is that it's not really intuitively correct. It's actually intuitively pretty incorrect. So what is the one thing that we know? One thing that we know is that every word has some fixed set of meanings, and then regardless of where this word appears in the text, right? The meaning of this particular meaning of meaning of this word in the context is going to be one of those fixed number of meanings. So what that means is that there is a moderate level of translation invariance. So let's imagine one word cat. So if you use the word cat at the beginning of the sentence, or at the end of the sentence, or anywhere in the sentence, it's almost always that you were referring to an animal cat, regardless of where it appears, right? Location doesn't really matter. Another word, llama, same thing. I'm pretty sure you weren't using the word for another, let's say, meaning. Or computer. All those things have a different meanings, or multiple meanings, but there's a small number of possible meanings. And then depending on where you are, it really doesn't matter, but it's always going to be from the small set of, let's say, the small set. But then here, the issue is that as we increase this n, right? So n refers to the input, right? As we increase the number of the parameters, this w that is associated with each and every one of these word embedding vectors, right? So here we have the number of the word embedding vectors put next to each other. And then you can imagine that instead of having a one W matrix, we have one matrix per location in the input. You can imagine it like that, right? What that means is that if you're not really saying that there is something that is shared across the different locations within this input, let's say phrase. And that just feels wrong, right? Intuitively, that just feels wrong. So let's just think about it once more. I'm going to give the example. So we said that we are going to use a column vector. So if we rewrite it, xt minus n, ext minus n plus 1, all the way to ext minus 1. Now what do we have here? We have a very large weight matrix here, right? We are going to have a very large weight matrix that is whose size is d prime, I, and d. And then what this means is that we have a d many rows. So we're going to have d many rows here. And then you can imagine that d prime many rows. And you can imagine that we have n copies of d prime by d matrix that is concatenated with each other. Now I'm going to call it w t minus n, w t minus n plus 1, all the way to w t minus 1. And what ends up happening is that we're going to sum over t going from 1, well, n prime going from 1 to n. And then we look at t minus n prime times e of x t minus n. So this is the procedure we're doing. And then what we see is that for each n prime, that is that how far the word is from the word that we want to predict now, we have a separate parameter. So you're in some sense, we're treating the word embedding, a word at each of the different locations completely separately from each other. So we're not imposing any kind of knowledge we have about language modeling, and then that is that there is a moderate level of translation invariance within text. Now, of course, you might think that maybe there's no translation invariance. But one thing for sure is that the cat, when you say cat, it's almost always the same cat that you're referring to, regardless of which location in the sentence you're saying cat. So is it all clear? Okay.
So can you explain how that captures that phenomenon?
It doesn't capture that.
Oh, okay.
Yes. So that is one of the two missing ingredients in this neural probabilistic model. One is that the size of the weight grows, so the number of parameters grows, and then relatedly, the second issue that comes together with growing number of the parameters is the fact that we are not imposing any level of translation invariance. While we know that there is some translation invariance, using word embedding actually was imposing a very strong translation invariance. Because word embedding of a word is same regardless of where it appears. But somehow we're not doing that in this next layer of the network. So far so good? Yes. So if the translation invariance is the lack of this moderate level of translation invariance an issue, now what is the right way for us to introduce that kind of translation invariance? And then one thing for sure is that the number of parameters cannot grow linearly with respect to the size of the context. As soon as it happens, that probably means that we are actually losing the property of the translation invariance in general, not perfectly so. So let's try to go back to the drawing board and then try to come up with a neural net-based language model that is not going to have these two issues. The number of parameters is not going to increase with respect to the size of the context of the input, so that we can actually apply this language model to arbitrary length, unbounded, let's say, context, right? So we want n to grow as large as we want. And then the second thing is that we want to introduce this kind of moderate level of translation invariance. To get there, we need to think about what text classifier actually does. So there was a reason why we spent the entire week on text classification, because it comes up over and over. And one way to look at what text classifier does is that it compresses or the summarizes input text. So let me just write down the text classifier again, assuming that the input was same as the sequence that has the t many words or the tokens. And then what it does is that if we just assume that we're going to use a continuous backover representation, the feature of x is going to be some sigmoid function. So we're talking about the nonlinear classifier here. W times t goes from 1 to t, embedding of each of the word plus b. And then given this feature vector, the score we assign to the class given the input is going to be uy, that is the class embedding of the y, transpose phi of x plus the class bias. What we notice here is that this phi here is working as if, so from the perspective of this score function, this phi of x is what the input is. So phi of x is what input is to this score function. And then somehow this phi of x is always turning the input sequence that can be very long or that can be very short into a fixed dimensional vector. Yes.
Sorry, where's the x in that expression?
Oh, I'm sorry. Yeah, so I used the W there. I'll change the W. So let's see, which one did I use? X. Okay. Good point. Good point. Let's use the X here. Yes. So what it does is that this function phi in this particular case uses the continuous backover followed by a one nonlinear layer. What it does is to compress the input with an arbitrary length into a fixed dimensional vector. Yes.
But this is again bag of words, right?
This is a backover.
But you said that wouldn't work in a
You could always replace it, but this is the example we use for the text classification. Right? So how you build this feature, again, this is the one thing that we talked about in the first week, is that how we extract the feature is domain dependent and problem dependent. And in this case, I'm just taking as an example where we use a continuous backover representation followed by one nonlinear layer. Okay. So what this phi of x does is to compress the input that may have a varying amount of information within it into a single fixed dimensional vector. And then how it does it? It compresses it by giving up or losing out any information that is irrelevant to solving this problem of text classification. So it is doing a task-dependent, lossy compression of the input. And then this is a pretty amusing thing if you think about it, is that somehow by training a text classifier on a data set that you have collected, you have somehow learned this compression function that's going to take as input a variable length sequence and then compress it down into a single fixed dimensional vector. Yes.
So this is classification where you have multiple different classes.
Yep.
Are all the classes going to be the same length, or would some classes need to preserve more information?
Yes. That's an interesting question. So the question is that It's actually an interesting question in the sense that does the class embedding have to have the same dimensionality for every class, right? So that's the question, because if that is not the case, and then for instance, if you want one of the classes to have a higher dimensional vector because it's more complicated or not, then this one has to change accordingly. Now, in the context of this course, the answer is no. So it's fine, because as long as we make a large enough, high enough dimensional vector for the class embeddings, then we can use the same dimensionality for all the classes. And then other classes that are simpler to model are simply going to use a very low dimensional point in this high dimensional space. So it's fine, but in reality, in fact, together with my PhD student and also a course instructor here, Ilya Kulikov, we're actually, and then Maxine as well, we're writing a paper about how to make the class embedding a set of vectors instead of a single vector. So right on the point, I'll try to share the paper once the paper is written, about a month or so. Yes. But good question. Well, for the purpose of our lecture, we're going to simply say that every class embedding is of the same length, same dimensionality, and then this P is the compression. Right? So what it says is that the neural nets, by being trained on the data, can learn to compress complicated stuff into a single vector. Then we're going to use that idea to build a so-called a recurrent neural net. And then the idea behind building a recurrent neural net for us, or the motivation, is to recursively compress the input. Then recursion is indeed at the core of computer science, so we're going to use that idea. The idea here is that we're going to simply assume that there exists a sum function or some function P that is able to compress the sequence. Let's use T minus 1. We're going to just assume there exists some P that takes as input this sequence, and then you have to result in some, let's say, the fixed dimensional vector. And then the question is, what is the right way to add another word? So when we have this HT, let's put it -1, if we have HT -1, and we add WT here, what is the right way to go about? Then perhaps we can just use a neural net to do it for us, right? So the whole idea of machine learning is that we don't know how to solve the problem, so we're going to come up with an algorithm that is able to solve the problem, but we don't know how to solve the problem, right? So that's the idea of machine learning. So what we're going to do is we're going to say that there has to be some machine learning neural net that is able to take as the input the previous representation. So the representation or the fixed dimensional representation of all the previous words so far, right? So W1 all the way to WT. And then this neural net is going to take as input this together with this vector, the WT. I'll use R to indicate that this is some kind of neural network. And then the output from this is going to be WT. And then both HT-1 and HT are going to be, let's say, some fixed dimensional vector. So what this neural net needs to do is a neural net that's going to take as input a d-dimensional vector, concatenate it with one of the words. So what are we going to use? We're probably going to use a word embedding, concatenate them, and then outputs the next representation that adds WT to W1, the previous words. So what would be one of the simplest way to implement this one, based on what we have learned from the neural probabilistic language model, is a very simple neural network, right? Such as R, HT-1 and WT is some sigmoid. So we're going to make it nonlinear. So it's going to be a nonlinear, pointwise nonlinear function applied to the affine transformation of the input. So I'm going to use the WR to indicate this recurrent wave matrix times HT-1 plus WX. I'm going to use X to indicate that it's the input wave matrix, WT plus some bias. So this one was RD. Let's just rewrite. So it's going to be embedding of WT. And then we can, and then what that means is that this recurrent wave matrix is going to be D by D. I should use a D prime, right? So let's use D prime. D prime, D prime, D prime. And then the embedding is D-dimensional vector. So we embed the new word WT into D-dimensional space. And then what that means is this input matrix has to be D prime by D. And then what is the dimensionality of this bias vector? D or D? D prime, okay. So you're all listening, that's very good. So if you had this kind of neural network, then what this neural network would do is to look at the concatenation of the HT-1. So the summary or the lossy compressed version of what has been received so far, and the embedding of the new word. So we're going to look at the concatenation and using that and then transform this concatenated vector to be a new D prime dimensional vector. And again, we never want to be linear. We always want to be nonlinear. And we apply some kind of nonlinear function, such as a rectified linear units or hyperbolic tangent function, as we saw earlier today. And then once we do that, we end up with a new vector, HT, that is, again, a task-dependent lossy compression of sequence that spans from W1 all the way to WT. And then we just apply the same thing over and over until we consume the entire sequence. Then it doesn't really matter how long the sequence is, right? It can be, in fact, as long as we want. It can just be an online, let's say, stream of data. And that's again out of the context of this course, although it's a very fascinating topic. Only thing that we need to think about further is that what should be the initial value of H. So it's a recursive function. So we can apply it as long as we have some H. But then at the very beginning, when we receive the very first word, we don't really have HT minus H1 minus 1, that is H0. H0 can be set pretty much arbitrarily. There are two major options. One is that you're going to say that the H0 is a D prime dimensional vector that is a parameter. So you can imagine the D prime of the H0 as if that's a bias vector. Right? So that is just learned. That is just updated using the SGD procedure that we talked about. Or, so this is one option, or you can simply say this just all zeros. Just say D prime dimensional all zero vector. It's very tempting to think that this is always a good idea. But it turned out, if you do some math, that these are actually equivalent. So it's just simpler to just say that, okay, all zero. That's all. So let's just look at a few, let's say, parameters here. So what are the parameters we have? We have WR, we have WX, we have the embedding. Embeddings are all parameters, and then B. Then what you notice is that the same set of parameters, WR, WX, embedding, and B, are used over and over for every location, right? So this is how we induce some kind of translation invariance. Modular level is not perfectly true. It's not translation invariance, right? Because it has to depend on all the previous words. So it's not perfectly translation invariant, but there are some level of the translation invariance that allows us to say that the cat at the beginning of the sentence is same as the cat in the middle of the sentence. And then the number of the parameters, fixed. The number of parameters we can really count, right? So we have the D prime square D prime square many numbers in this WR. We have D prime times D many numbers in this matrix WX, and then we have D prime many numbers in this bias vector, and then the embedding, we also know how many of them are, and then it's fixed. It doesn't really change. Even if the input length is, let's say, 100, the number of the parameters is fixed. Even if the input length is 2, the number of parameters is fixed. So in that sense, It's much more reasonable, and they can really handle unbounded, let's say, length of the sequence. And then how about the computation of complexity? So the memory complexity constant with respect to the length. The computational complexity. So we can look at it from two different, let's say, cases. One is that what is the computational complexity at each time step? At each time step, the computational complexity is assuming that the d prime and d are in the same order. Is going to be quadratic with respect to d. But then the thing is, often d is only 200, 100, or 1,000. So quadratic of, the square of 1,000 is just million. So we don't really care these days anymore. So it's effectively a constant type operation every time we receive a new word. And to process the entire sequence, it's just linear. So all we need is just a single sweep through the words in an input sequence to get a single vector at the end. That is the compression of the entire sequence, however long that is.
Sorry, could you explain that complexity?
Which one? Memory.
Why it's quadratic?
Oh, why is it quadratic? Is because of we have a matrix vector product. And then we're assuming that the d's are all just of this d prime, d's are all of the same order.
How is this translationally invariant?
So this part, right? So how we consume this word, we use the very same function at every location. So that's the translation invariance. So regardless of whether we are in the beginning of the sentence or whether we are at the end of the sentence, we're going to use very same function applied everywhere.
We're summing up the W's with like previous ones, right?
No, where are we summing anything?
W are like times HT minus 1.
Yep. So this operator is how we apply this operator is translation invariance, and wherever it is, we use the exactly same operator, but the result is conditioned on all the words so far. So if you think about the individual word, right, then it is not perfectly translation invariant because the context is going to change or to choose the one of the many possible meanings. Right? But it's still largely, so the mechanism is perfectly translation invariant, but the actual content is only moderately translation invariant because this recurrent weight might easily ignore the history. So it's going to be very selective. Okay, now we know how to compress it. And then the nice thing is that we can compress the prefix for any sequence one word at a time, right? To compress whatever has been seen so far into a single vector. Then what was the thing that we learned is that to do language modeling, we do text classification. Then to do the text classification, there were two things that we needed. One is compression of the input. So the one was this compression of input. And two was this scoring function. It is simply computing the dot product between the class embedding and this compressed representation of the input. Now here, we actually already have it. So let's imagine that we get the stream of input words. So this will be W1, W2, W3, W8. Now we're going to apply this function R, starting with the all zeros. And it's going to give us H1. And then this R is going to be used again, and then give us H2. This slightly different arrow. And the R is again going to be used when the W3 comes in, together with the H2. And that produces H2. And it goes on and on and on. And if you think about it, these vectors, H1, H2, H3, are the compression of the words that have been received so far. So H3 is a compression or the compressed representation or fixed dimensional vector representation of W1, W2, W3. In other words, just running this recurrent neural net already solves the half of the problem. And all we need is to just put this function n on top of it. Now, how do we do that? Let's think about, there are many different ways to do it, obviously. But imagine that I'm going to have the f. It's going to take as the input this representation of the what has been received so far, so W1 to W3, and then it's going to look at the W4 to score it. So this is how you get the score. Because what is this? This is the correct class. This is the correct class in this text classifier. And we can use the same F again everywhere. So it takes us into H2 and the correct class that is the W2 and the output score. Same thing with the first application as well. We can just do it over and over. So what this actually tells us is that all we need to do is to read the text one word at a time, feed it into R, together with the whatever the representation we had from the previous time step, and then predict the score of the next word. And then we do it over and over. So all we need is just a one single sweep through the text that we want to score, and then that is going to be our language model. And this is called a recurrent neural net language model. Neural net. And then this was made popular by Tomasz Mikolov from in 2009 or 10 or something like that. His dissertation is really a tour de force of how to build a recurrent language model and then use it in a larger scale. Not the large scale of the modern era, but back then he was coding and running experiments all on his laptop. And they of course, on a laptop from 2009 is not the laptop where you want to train this language model, but he really optimized the hell out of everything. So it could run experiments by training these recurrent language models on Wikipedia, entire Wikipedia on his laptop alone. I still cannot believe that he has done that. All right, so then, once we know how to build a text classifier, we know how to train it.
Yeah, so like how meaningful are the compressed representations of those first words? Like what does that even?
Well, it's still, let's think about the very so the first one. So you can imagine that we thought about the counting, right? So something like if I told you that okay, the first word of this sentence is I, what should be the next word? Anything? No, you come to the though there, right? You come to period. You can, but you probably want a period. A lot of things, but it's actually much smaller than all possible words in that. So the most likely M was, and then you have all those verbs, right? But if you think about how many verbs there are compared to nouns, it's actually a really, really smaller subset from which you can. So yes, obviously having more context often helps. Not necessarily like this, but often it helps. And then even having one word or even having 0 word also helps. So that there has to be a 0 word, right? What is the 0 word case? Is where we apply the same F, but with the 0 as input. And then using the first word as the correct one.
Not just like this scoring function.
Yeah, to a scoring function. And then we use the scoring function, we use the score for every possible classes or the words, and then we apply the softmax function and then we put the probability. Yes.
Do we store the F anywhere? Does it have like a dimensionality to it?
Yeah, I mean the F is here. We already talked about it, right? That is
Yeah, what's the dimensionality of that?
what should be the dimensionality, right? So there's this P of X here returned, so that's the R, right? That returns D prime dimensional vector. So then what should be the dimensionality here? So this is the D prime dimensional vector. That means that our class embedding, so the next word embedding should be D prime dimensional vector. And then what should be the CY? It should be just a scale. So in fact, the score is just a one dimensional scale. But we get it for every possible next word. We can compute that for every possible next word. Question there?
Do we like update W's at each and every step, like gradient descent?
Well, so how would you actually do it? If you think about it, now this actually goes all the way back to the here, right? So if you look here, what that means is that in order to compute the log probability of a given text, we have to compute the log probability of the next word for every word. And then that's our loss function, per example loss function. So what will we do? We would compute the entire thing and then trying to compute the gradient of this per example loss function, or that is the gradient of the average of the per example loss functions with respect to the parameters. So we wouldn't update the parameters on the fly. We can, yes, we can, but we wouldn't do it in practice. I mean, that's another fascinating thing that we can talk about, but just really, we don't really have time. If time permits, at the end of the course, we might be able to talk about how we can train a neural net in an online manner. That's definitely possible. So one thing I want to just quickly point out here is that if you look this one, right, and then trying to look at it from a slightly different angle. So you're going to look at it from the side. What you notice is that this is really just a very, very deep neural network. Right? This is a very, very deep neural network. And then the depth of the neural net is same as the length of the input sequence. And at every layer, we every layer takes the input and also makes a prediction. This is just a very, very deep neural network that we're building. And every layer shares the same set of parameters. What that tells us is that really all we need to do is to use the exactly same thing that we use in order to train any kind of text classifier. That is, we will go forward all the way, make all these predictions, and then based on the prediction, we can compute the log probability of the correct answers everywhere. And then we sum them because the sum of the log probability of the correct next words corresponds to the log probability of the actual input text. Then we use a backpropagation algorithm to backpropagate the error or the loss on the gradient all the way through the entire thing. And then we update the parameters. Only question here you might ask is that if, so let's say the WR, WX, D, as well as all these class embeddings, UYs and CYs are shared. They are used at every layer. So what is the right way to compute the gradient of them? Yes, backprop. So backprop, but then you can imagine having this as this is another one. Confusing. So let's say the here are parameters WR. Not the best choice. WR, WX, then B, and then Y, and then CY. So these are all used everywhere. And then every layer. Right? And this will be used here, here. So when we do the backpropagation, what happens? So we're going to backpropagate the error little by little, and every time we need to pass it through the parameters. So we get an error coming from all the layers. Now what do we do? Calculus 101. Calculus 101. Sorry. Yeah, chain rule is backpropagation. Okay. Calculus 101. Yes, and then indeed the chain rule is actually one of the most important thing in Calculus 101. But in this context, something slightly different. So what do you do? You get the error coming from this layer to B, and this layer to B, this layer to B. Sum them, right? Sum them. Okay. I don't know. Only about 1/5 of you were confident in answering, but you simply sum them, right? So the reason why you sum them is just based on the calculus, but sometimes it's a bit confusing. Now, this is the recurrent language model. You now know how to build it, why we built it, and how you train it. Is there any questions on this? If not, we're going to take 5, and then we'll come back, and then we'll talk about the evaluation and the language model is in the context of the compression.
Yeah, kind of.
Everyone, you should ask. No, please, it's okay. Take as much time as No, this is just
I think that's really bad. It's like 20 hours a week. Yeah, that was
okay, right.
yeah.
Okay, so everyone is back. So last week and lab session. Okay, all right. Not high school anymore. So the last week you learned about perplexity in the lab session, what perplexity means, and then you learned the fact that the perplexity is something that we use in order to measure the quality of a language model. And then I checked the lab session, the material, because we always review it together between the course assistants and I. And then I thought it was pretty well explained. But there were some questions about the perplexity and then why we use perplexity and then what it means to compute the perplexity. So I thought I'm going to use the half of today's lecture to talk a bit about a bit different way to think about what language model does, in particular this kind of recurrent based language model does, and then why we started using perplexity. And the interesting thing is that this whole thing was already written down in a paper in the 50s by Shannon. So we're going to talk about a bit of information theory because it turned out that the machine learning, information theory, programming, all the same thing at the end. Let's assume that we're going to have two friends who are talking to each other. And we're going to say we have Alice and Bob. And then what we are going to assume is that we're going to just look at one particular time slice of this conversation they are having. So in this case, now Alice wants to send a message to Bob. So Alice wants to say, say something, and then we're going to assume that there's only C many possible messages Alice can send. So we have Alice, and then Alice wants to send some message to Bob. This message can be one of these script tokens. You can imagine that Alice has a chance to say one thing to Bob. And then that can be one of the words in the vocabulary. Now, in order to send this message to Bob, how many bits does Alice need to use in order to ensure that her message was sent to Bob well enough? Log of what? M. Log of M. Well, is it true? If I decide to send a message of 1, then I don't have to send any bit?
Yeah, log of the number of possible.
Okay,
Yeah,
log
yeah.
of C. Okay,
Yeah.
log of C where the base is 2, right? So that's probably what we always learn is that if you want to send one of the C many possible messages, so Alice needs to use log 2 of C many bits. With let's say we do some kind of sealing, right? We're going to do some kind of sealing. Or we're going to say that the C is always the to the power of some number. But what does this mean? Why does Alice need to use log 2 of C bits in order to tell Bob one of these messages? And can actually Alice use a fewer than log 2 of C many bits to send a message to Bob?
You can see the number of words.
No, this is, so there are C many words, and then Alice is trying to send one word. One word to Bob. So Alice just wants to send one word. Yes.
You can get the probabilities of each word, the statistical, how many probability of a word occurring, and then assign fewer bits to that one, and assign higher bits to the words which occur rarely.
So why is there a good strategy? Why is there a good strategy? So let's talk about. So that's the answer. Except that you have to think about why there is a good strategy. Right? So what would be the case where the Alice and Bob, Alice doesn't even have to send any message to Bob, and then Bob still knows.
She always sends a sentence.
Yes. But even better, if Bob knows already what Alice was going to send, if Bob knew what Alice is going to send, obviously Alice doesn't have to send anything because Bob already knows what Alice is going to send. So we always start from there. If Bob doesn't know anything about Alice or what Alice is going to send, Bob can't guess, okay? And then you have the message can be any one of these C many possible words. But if Bob knew exactly what Alice was going to say, then we don't really need for Alice to send anything because Bob already knows. Right? So we start from there. What we start from there is that if Bob does not know Alice at all, then we do need log 2 of C is on expectation, or actually always, because the best way to encode is to starting from using a binary. So we're using a binary encoding, is to say that build a balanced binary tree. So we start from the root, then we're going to say on this side 0, on this side 1. Then we're going to go for each of the case, the binary node, right? 0, 1, all the way. And then at the end, in the leaf node, each and every leaf node corresponds to one of the messages. And then the number of the bits we need in order to send any one of these messages is essentially the depth of this tree. And then when we have C many leaf nodes, then we need the depth is going to be log 2 of the number of the leaf nodes in the case of balanced binary tree. And then the reason why that is so is because Bob has no idea what Alice is going to say. Bob cannot really guess anything about what Alice is going to say. Now it turned out that's actually to turn it around. If Bob knew Alice really, really well, so Alice and Bob are really good friends with each other, so that if Bob can largely guess what Alice can say, then we can start rearranging this whole tree in a way that according to how likely. Okay, so I'm kicking him out actually. Yeah. No joke during the lecture, except for me. I'm a lecturer. All right. So what we're going to do is we're going to rearrange this binary tree. We're going to rearrange this binary tree in order to ensure that we don't have to use too many bits to send all these things. Now, what does that mean? What does it actually mean to do so? And then why would we do that? Let's imagine that the Bob knows that there are only 2 possible messages that Alice is likely to send to him. Right? Now, what that corresponds to is that what is the probability of one of those 2 tokens, 2 words that Alice is going to send is going to be 0.5 and 0.5, and then all the others are 0. And what that means is we really don't need, let's say, log 2 of the C many bits. All we need is just 1 bit. Why do we need just 1 bit? Because we just need to distinguish between those 2. Let's say there were 3 of them. So instead of the all C of them, Bob already knows Alice so well that Bob can guess that it's always going to be one of these 3 words that Alice is going to say. Then what Alice needs, again, is only 2 bits, right? To tell Bob what she wants to say. And then what this says is that if we want to know for each of the possible words, if the Bob knew how likely that word, I'm going to if Bob knew how likely that the message is going to be sent by Alice, right? Relatively, because it's probability. What Alice needs to use is the log 2 of the log 2 of the chance of the message being sent. That's what Alice needs. And then we're going to look at the expectation. So, of course, this can be very long or very short, depending on the probability. You see the sign, minus sign there. So if the chance of M is really low, so the Bob's guess of what Alice is going to say for that particular message was extremely low, then minus log 2 of this will be extremely high. If Bob thought that with a chance of 1, that Alice is going to send me this message, and that turned out to be true, then you need 0. And then what this tells us is that if Bob can guess well, and then that corresponds to the actual chance of the Alice sending the message, this is the expected number of the bits that we will see if the Bob and Alice know each other really, really well. So Bob can guess exactly what is the chance that the message that is being sent by the Alice is going to happen. Now, let's see. So, and then you have this is what we call Shannon entropy. So this is the entropy, and then if the entropy is high, what does that mean? Is that the expected number of bits that needs to be used to send a message from Alice to Bob is many. If this entropy is low, that's the other way around. And then how can this that happens is that this corresponds to how many messages are likely to be sent by Alice. If there's only few, then it's going to be really low. If there's many, it's going to be high. But again, this is all assuming that the Bob and Alice agree on this probability distribution over the message. And what we now want to look into is so-called cross entropy. What if the chance of the message actually differs between what Alice distribution and the Bob's distribution? Then how will we know that the Bob is making a good guess of Alice in this setup? What we want to do is that we're going to just look at the number of the bits that Alice is using in order to send a message to Bob. And if the number of bits is really, really high over time, that just means that the Bob doesn't really know about Alice, despite the fact that Bob thinks that the Bob knows about Alice, right? So what that means is that we are now going to look at the number of bits that Alice needs to use in order for us, for the Bob, to understand the message that Alice is sending. And then that corresponds exactly to the idea of the low probability or the negative low probability of the correct word. Now, when we train a language model, let's look at this one. When we train a language model, that language model represents our understanding of what the writer of the text would write, how they would write. What would be the word that the writer would say, right? That's what language model does. And then the language model that we trained, because we trained it, so that is our understanding of what the writer is going to say. And if our understanding, if our prediction is perfect, number of bits the writer needs in order to send us the word is 0. They don't have to say anything. We can just predict it perfectly. All we need to do is we just ask our language model. And if our language model says, oh, this word is going to the next one, then we know that there is a word, because there is a word. But that's often not perfect. Now, how to check the imperfection of this language model is to see how many bits we need in order to encode, in order for a writer to encode the word and then send it to us so that we can recover the original word. And then that corresponds to negative low probability. Yes.
We only use log base 2 because we're talking about bits.
Yes, we're going to get there shortly, yes. So that we use log base 2 in order to get into the bits, right? So if you look at that binary tree, if we decided to use not the binary tree, but some n-ary tree, then we're going to just use the log of base n. So it can be in fact arbitrary. It's just that I don't know why, and then, whether that has to be the case, but it's a convention that we often use in order to study the computer science and algorithms now. That's a good question. I don't know if there is a fundamental reason why it has to be this.
It's also neat, right? You use N, not sure.
Yeah, you can use the nets, you can use any arbitrary thing and then you name it yourself and then that becomes the name. So it can be really arbitrary.
I think the same theory applies to information gain in decision trees, which is
Yep.
where this comes from.
Exactly. So negative low probability of the correct answer corresponds to how many bits our oracle, who knows the answer, right? Who knows the answer needs to, how many bits the oracle needs to use to send us what the correct answer is. If our prediction is perfect, we don't need the oracle to send us anything. We don't need anything. If the prediction is very bad, oracle will have to pay a lot of bits in order to tell us what is the right answer, right? And then if you go back to this figure, that's precisely what we're doing. The language model starts with nothing, tries to guess what the next word could be, right? And then if our prediction is good, the actual writer or the oracle needs to pay only a small number of bits, only a few bits, to tell us what the next word is. Now, given that one, our language model is going to try to guess what the next word is going to be. If our guess is good, the oracle needs to send us only a very small number of bits. But if our guess is bad, then oracle needs to use many bits. Now, what is the worst case? What is the kind of, let's say, reasonable a priori worst case is that we have no idea. We say that everything is equally possible. That's when you get the log 2 of the vocabulary size many bits for the oracle to send us the exact one. But as we get better and better, and then why do we get better and better in this sense? Is because we actually try to minimize the number of bits needed for oracle to send us the correct answer. Okay, so far so good? Or no? So what it says is that what we're trying to do by training this neural network, in particular in this kind of, let's say, language model setup, is to minimize the number of bits needed for an oracle who has already written the text or they found the answers to send us the correct answer or to tell us the correct next word. So that's what we're trying to do. And then thereby, this language model is going to minimize the number of bits that are needed for the oracle to send us the correct one. But then, it's really not really interpretable. The number of bits you need to, maybe not even you, right? The number of bits an oracle needs in order to send us the correct answer, the correct next word is a bit uninterpretable. So what we often want is to turn this around just a bit by saying that how many predictions we need to know, or how many words, next word, or the correct answers we thought were more correct than the actual answer sent by the oracle. So we're making guesses. We're making a lot of guesses. Our model is making a guess over what should be the next word. And then now Oracle sent us the actual word. Oracle revealed the true word. And then now we can look at how many words we thought were more likely than the actual one. So that we're translating the number of bits we need our oracle to incur, as opposed to minimal number of bits that Oracle could have incurred had our prediction been much better. So that's what we want to know. So how many words we thought were more likely according to our language model than the correct one. And then that's the perplexity. So what we do is we're going to turn this negative log probability into a perplexity by exponentiating it. Yes, so we do this, and then let me just write it in the language model context. So in the language model context, it's going 2 to the minus log 2 of P of WT given all the words before. And then now this one suddenly refers to the number of more likely words under our language model, our predictor, given all the previous words. So if our prediction was perfect, the correct word that was revealed to us by Oracle, there wouldn't be any other words that are more likely or more probable under our guess than that word, right? That has to be the top one. So that's why this perplexity is going to be 1. So because if we put the probability of 1 on the correct word. But if there are some confusion, uncertainty, even if we have a perfect prediction, it's possible that there could be, let's say, 2 perfectly reasonable answers. In that case, what's going to happen is going to be half. So 1 over 2 over 2 possible answers. And then what is the log 2 of the 1 over 2? Minus 1. Minus of the minus 1 is 1. So we can perplexity of 2. What it says is that there were 2 probable answers given this Oracle's actual revelation. So even when that's a perfect thing, you get that kind of cost, right? So this makes it a bit easier for us to understand. And then one thing that you notice here that is connected to the question earlier is that what you notice is that the base doesn't really matter as long as they match each other. We could replace it with the exponent, or we can replace it with any number that you want as long as that is positive number. So, but of course, this is for one prediction, but we are not only looking at the one prediction, we are looking at many predictions because we want to get a better estimate of how good our prediction is. In that case, in language model term, we're going to look at n many sequences. And then for each sequence, we have a different length, let's say t to tn. And then we look at log 2 p of wtn given w, all the previous words in the nth, let's say, example. And we compute the average. Look at the negation of that. I'm going to use b. So this you can think of it as the average number of bits that are incurred by the oracle to send us the correct answer. Then we exponentiate it. We exponentiate it to get the perplexity. Yep.
Is that a W raised to the K?
And so the
So
n.
those are both N's.
Yes. So that's from the nth example.
Sorry, why are you summing t's to the power of n?
Oh, so this one, so this is not the power, but this is the t of the length of the n example. So this is just getting all the predictions that we have made, or all the bits that we have paid for every word in the book. So how we evaluate language model is not too different from, let's say, how we evaluate the classification, but the one major difference, or the one major kind of subtle difference you notice is that in the case of classification, we often assume that there is a single correct class to which the input belongs. Now, in the case of language model, that's not necessarily true. It's almost always that there will be multiple possible answers. Then that's the interesting thing about this kind of unsupervised learning, because we're looking at an entire input space. There are many different answers that make sense. So it makes more sense to look at this kind of perplexity. That is, given the correct answer that we have seen, how many more words the model thought were more reasonable. Now, it's good if the perplexity is low, so there were fewer of them, but this number does not have to go down to 1. And it's very likely that if it went down to 1, there's a bug. Yes.
So you always measure the model's complexity in relation to the training set of words that it was trained on?
No, you compute it on the validation set.
Okay, I see.
You compute it on the validation set and the test set, not on the training set. On the training set, you can actually, if you make a model large enough, you can get the perplexity that is close to it. So this is where the perplexity comes from, and that is the reason why we use perplexity in order to evaluate a language model. So we're going to use the perplexity for many occasions. Now, one last thing that I wanted to point out is that if you look here, this is slightly different from the loss function that we said we talked about last week that we should use for training a language model. What's the difference? The difference is that last week it was the average of the sum, because we're looking at the average of the log probabilities of the sequences. Now here is slightly different in a sense that we sum all of them, but when we average, we actually average over not only the sequence but also the tokens as well. So there is a slight difference, and then depending on the distribution of the length across the sequences, there could be some difference between this, how we compute perplexity, and how we compute the language model loss. Which one is better? Depending on what you want to do. What you care about is just to focus on the predicting the next word, then you can actually try to minimize this value variable. If your focus is on to computing the low probability of the entire sequence, what we talked about last week makes more sense. So that's actually the whole, let's say, content of the space vector. Is there any questions?
Are they both related in the sense?
They are related, yeah, they are related in the sense that if the length of all the sequences is the same, then they're going to be same. But if the length differ, they're not necessarily the same. So that's it. Since we have, let's say, a few minutes, let me actually ask you a couple of questions. I'll start with